Hi, today we are going to introduce Auxetic 2D, a plugin for automatic modeling of Auxetic metamaterials in the Abaqus software. But what are Auxetic metamaterials? Well, metamaterials are a class of materials that have a property which is not found in nature. These properties are not because of the underlying base material, but a result of the way it is arranged. What happens is that a unit cell with a certain geometry, size, and orientation is designed and repeated to form a structure, which then exhibits very useful acoustic, electromagnetic, and mechanical properties. Auxetic metamaterials are a class of mechanical metamaterials that exhibit a negative Poisson's ratio, that is, they expand when compressed and contract under tension. Auxetic 2D is a plugin for the Abaqus software which automates design, analysis, and manufacture of 2D auxetic metamaterials. In this video, we will present the software's capabilities using an example. Let's solve the following problem from the field of auxetic metamaterials. Given an auxetic structure created from a reentrant unit cell, which is shown here, what is the effect of theta angle on Poisson's ratio? And does Poisson's ratio change during loading? And let's assume that the material is TPU and simulated using the Marlowe model. Now the parameters are as follows. Our unit cell is a reentrant unit cell. And the material is TPU, which has the stress strain as shown in this curve, and the material will be modeled using the Marlowe strain energy potential material model. And 20% strain will be applied in the y direction to the structure. The structure will be constructed using the following parameters. Its total length will be 100 mm and it will contain 6 unit cells. And each unit cell has a height to length ratio of 0.5 and 3 values for theta, 65 degrees, 70 degrees, and 75 degrees. And finally, the struts in the unit cell will have a thickness of 0.5. Now, to perform this analysis, we have to create 3 models with different theta angles. And this is very time consuming. It can take at least half an hour to model, and then the analysis will have to be performed, and finally we have to post-process the results to determine the resulting Poisson's ratio for each model. But Auxetic 2D can perform all of the modeling and analysis automatically. Let's see how it works. First, we need to install the plugin. The plugin comes as a zip file containing the code and a PDF of the software's instructions manual and documentation. In order to install, we will copy the folder containing the code, and now we need to paste it into the Abaqus software's plugins folder. To find it, we will go to Drive C, which is where Windows is installed, and find the folder named Simulia. This is where Abaqus is installed by default. Here we will navigate to CAE 2017, which is the version of Abaqus running on this machine. Win_v64 code, Python 2.7, lib, which stands for library, and finally Abaqus_plugins. I already have the plugin here, so I'm going to delete it. And now we need to paste the folder that we copied before here. Now this plugin will be recognized by Abaqus as soon as we restart the software. I do not have the software open, so I don't need to close it, and as soon as I open it, the plugin is available for our use. Now, after opening the Abaqus software, we will click on the Plugins menu and open our plugin by clicking on its name. The graphical user interface consists of 4 tabs which are used consecutively. First, we will create our geometry in the Topology tab, which is the first one. Here we can select from a number of different unit cells. We want a reentrant unit cell, so we will click on the reentrant radio button. Now we can select the geometry parameters based on our example. First, we need to specify the number of cells we want in our structure. We use the slider to select 6. Next, we need to select values for the height to length ratio and the theta angle. Here we can request multiple models to be created and analyzed. There are 3 sliders and we can input a starting value, a number of steps, and a final value. We only need a single height to length ratio of 0.5, and as such we select that as both minimum and maximum, and we leave the number of steps as 1. So this should be 0.5 and the maximum should be 0.5 as well. But we need 3 values for the theta angle, 65, 70, and 75. So we select 65 as the initial value. We select 2 as the number of steps. And we select 75 as the final value. As for the strut thickness, we will set it to 1.5. Next, we go to the second tab titled Geometry for 3D Printing. This plugin can output a STP file suitable for 3D printing. First, length of the part is specified. This must be selected with the size of the print area in mind, so our printer can make it. Let's leave it at 100 millimeters. To perform a good experiment, the part needs to have a certain amount of thickness, which is selected next. Let's set that to 10 millimeters, which is a centimeter. Finally, we need solid ribbons at the 2 ends of the part, which can be fixed in the testing machine. Thickness of these ribbons is entered next to be 20 millimeters. This has no effect on the simulation. The third tab is titled Material. Here we can specify 3 material models. The first is an elastic model. The other 2 are hyperelastic models based on the Marlow or Ogden strain energy potential material models. As we mentioned earlier, we are going to use the Marlow model, and therefore we select the hyperelastic radio button here and the Marlow model from this drop-down menu. The stress-strain data can now be copied into the table. We simply select the data from our Excel file, copy it, and then paste into this table. And we are done with the material properties. The final tab is titled Analysis and Optimization and finalizes the process. First, we can choose a name for the job, which is also used for all other output files. Afterwards, we can choose the extent of the operation. We can ask the plugin to simply model the structure, or to additionally run and perform post-processing, which is what I'm going to select. In order to run the job, we must specify the loading direction, which based on the problem parameters is the Y direction. We also input the strain applied to the structure to be 20% and ask the software to output the value in at least 4 different intervals. If we increase this, the size of our output database will be larger, but I'm going to leave it as it is. Finally, we specify the ratio of mesh size to strut thickness. I'm not going to change this because this is okay for our problem, but you may want to change this for your problem. This plugin can output multiple files and variables. Poisson's ratio for the structure can be calculated based on a mean Poisson ratio model or a middle point Poisson ratio model. This is described and investigated in the instructions manual. I'm going to leave both of them on, so both of them is reported to me after the analysis finishes. A step file can be exported for 3D printing. This can also be converted to a STL file, which is described after this is finished. Finally, we can ask a number of MATLAB plots to be output for analysis. These will be outputted as an M file, which needs to be run in MATLAB in order to export our plots. After we're done, we will click OK to run the analysis. Now some time has passed and the analysis has been completed. Let's see the files. This is the temp folder used by Abaqus. Here we can see two models, Auxetic 0, Auxetic 1, and Auxetic 2. The respective ODBs can be used for any post-processing that we wish to perform. Also, a STP file has been created by the plugin for each model. These can be used for 3D printing the models and then performing experimental procedures on them. To do that, first we need to import the STP files into Abaqus. First, we create a new model database. This closes our database and we have a blank workspace. Then we go to the File menu, click Import, and import part. The file filter has to be set to STP, and now we can select any of the three files. Let's select Auxetic 2. We can set a name and the other settings and then click OK. The part has been imported and can now be output as a STL. To do that, we need to go to the Plugins menu, select Tools, and STL Export. Then click OK. This may take a while, but after that, the STL can be used in any slicer software to produce G-code for your printer. Let's take a look at the output databases. Here we have Auxetic0.odb, which is the output database for the model in which theta was equal to 65 degrees, and we have the Mises contour at various stages of deformation. This is 0% strain, 5%, 10%, 15%, and 20%. It is obvious that the model has a negative Poisson's ratio because barreling occurs, and if we zoom on the unit cell, we can see that the unit cell changes shape with different values of strain. This is 5%, 10%, 15%, and 20%. And this should be different for each structure. Next, we will look at the ODB for the model in which theta was equal to 70%. Here's the ODB for Auxetic 1. And again, we can see that at 0%, this is the initial structure, 5%, 10%, 15%, and 20%. And again, if we zoom on the unit cell, we can see this change, 5, 10, 15, and 20%. It is obvious that Poisson's ratio changes during deformation for both structures, and the same applies to the third structure, but I'm not going to show that because it's the same. but we cannot answer whether the Poisson's ratio changes. We know that they're both negative, but from this ODB and without further post-processing, we cannot determine Poisson's ratio. We have to perform some kind of post-processing, which can be performed in Abaqus, but the plugin can easily perform that. Let's see the post-processing done by the plugin. In the last tab of the plugin, we had requested Poisson's ratio and deformation history to be output, and the plugin has done that using 3 M files, which I will now run in MATLAB. To do that, I will open MATLAB and then navigate to the folder in which these M files are present, and then right click on the first one, which is data Auxetic deformation, which is a deformation history. Right click on it and click run. This may take a while, and after that the plots related to deformation history are shown to me. So here we have displacement of different points of the structure for different auxetic structures. This is the one where theta was equal to 75%, the one where it was 70%, and the one where it was 65%. Now we can see here that in the lower values of theta, displacement is higher, and then it is lowered in the 70 degrees, and the one with the highest degree has the lowest amount of displacement. Of course, we could have done that for the height to length ratio and study that, but our example was only studying the theta value. Next, we will check the Poisson's ratio. We had requested output of Poisson's ratio in 2 methods. One where the mean value of Poisson's ratio was calculated, and the other one in which the Poisson's ratio based on the middle point was calculated. Now these 2 methods are different, and the difference is outlined in the PDF file accompanying the plugin, but we are only going to work on one of them because the analysis is the same, only the values may differ slightly. So I will right click on it and click run. So here we have mean Poisson's ratio as a function of strain for the different structures. The one in which theta is 75 degrees, 70 and 65 degrees. It is obvious that for all of them, Poisson's ratio changes as a function of strain. It increases with strain, but the values are different. For instance, for the model in which theta was equal to 65, the Poisson's ratio in the initial structure is minus 0.16, but in the model in which theta was 70 degrees, it starts at minus 1.25, and in the other one it is 0.085. So as theta increases, the Poisson's ratio in fact increases with it. It becomes less negative. It becomes less auxetic, if you might say. And the end point also decreases. In the model in which theta was equal to 65, it ends at minus 0.13, but the other ones it ends at minus 0.09 and minus 0.05. So this is evident that as theta increases, the model becomes less auxetic. Poisson's ratio throughout the loading history decreases. Now the other outputs are Poisson's ratio at different strains for each theta. So here we have Poisson's ratio for different values of theta 65, 70 and 75 at 20% strain, 15, 10 and finally 5% strain. Now here we can see the same conclusion that as theta increases, Poisson's ratio in fact increases and it becomes less negative, less auxetic if you might say. But again, at different values of strain, the values are different. For instance, if we have 10% against 20%, and we can see that for any part of that, the Poisson's ratio changes. This is the same conclusion that we drew before. Now, all of these conclusions can be drawn from the ODB. Nothing has been done here that cannot be performed in Abaqus. But all of this was enabled by a checkbox in the plugin, and all of this was performed automatically. If we wanted to do this analysis and draw these numbers from a single structure, it would have taken us at least 15 minutes, and maybe we had made some errors, but this plugin makes it very easy, very straightforward, and reduces the rate of errors which can possibly ruin our work. To summarize, the problem could be solved using the Abaqus software. Auxetic 2D performed modeling using a small number of parameters. Multiple analyses were performed using Auxetic 2D automatically. And post-processing was also done automatically for all models. This plugin saved us a lot of time and reduced the rate of human errors. To get a copy of the plugin, contact us at j.cat@srttu.edu, and questions, suggestions, and comments are very welcome. Thank you.